This is your presenter Asloob Mudassar, and I am presenting slide number 92 of the course on laser physics. Question is, discuss the physics of unstable resonators with the geometric optics point of view and wave optics point of view. The answer is, in the G1, G2 plane, the unstable regions are those for which G1, G2 is greater than 1, referred to as the positive branch resonators, and G1, G2 is less than 0, that is the negative branch resonator. These regions have been indicated in figure 1. You see that we are plotting G1 on the horizontal axis, G2 along the vertical axis, and we have shown 4 quadrants. In the first quadrant, we have G1, G2 is greater than 1, and similarly in the third quadrant, we have G1 and G2. The product of G1, G2 is greater than 1. In the first quadrant, both G1 and G2 are positive. In the third quadrant, both G1 and G2 are negative, but their product is positive. So you see that the region G1, G2 greater than 1 for the quadrant 1 and for the quadrant 3 are the regions of unstable resonator, but with a positive branch resonator. So these are called positive branch resonators because here the value of the product of G1 and G2 is greater than 0. And in the second quadrant and in the fourth quadrant, you will see that the product of G1 and G2 is less than 0, both for the second quadrant and for the fourth quadrant. So here these two are also the regions of the unstable resonators. And you see that in this region, these regions are also called negative branch resonators because the product of both G1 and G2 is less than 0, that is negative. Now look at the two curves represented by G1, the product of G1, G2 equal to 1, the curve given in the first quadrant and also the curve given in the third quadrant for the value of the product of G1, G2 equal to 1. These two curves are actually at the margins of the stability. And you see that between these curves and between the axes G1 and G2 axes, you can see the dots, the black dots, and black dots are actually the indication of the stable region. So the caption of the figure 1 is indication of unstable region, that is the regions without dotted area. Thus the regions in the dotted area are the regions of stable resonators. So you see that here in this question we are going to discuss unstable resonators. It means that either we are talking about the region for which G1, G2 is greater than 1 or G1, G2 is less than 0. That is, we are talking about the quadrant 1 and 3 and the quadrant 2 and 4. For quadrant 1, we have positive branch resonators, and for quadrant 1 and 3, we have positive branch resonators, and for quadrant second and fourth quadrant, we have the negative branch resonators. So more detailed in this answer will be given about the positive branch resonators. And you see that this is the stability curve for the resonators, and we have discussed this curve in many of our previous slides. So if you want to have a greater detail, look at previous slides. That is the foregoing slides. And you know that G1 is actually, we have defined G1 earlier as G1 is equal to 1 minus L over R1. And G2 has been defined as 1 minus L over R2. Well, L is the separation between is the length of the resonator, and R1 and R2 are the radii of curvature of the two spherical mirrors of the resonators. So G1 was defined as 1 minus L over R1, and G2 was defined as 1 minus L over R2. Sometimes lasers designed in stable regions are limited in optical power due to small size of beam spots, and this small size is due to the placement of a small resonator aperture. A small resonator aperture is placed within the resonator to obtain a TEM00 mode, which is transverse electromagnetic mode, 00 mode. You see that this is the best mode in the laser, and in order to generate this mode, we need to place a small resonator aperture, and this also limits, this also makes the beam spot to be smaller, and of course the optical power is also limited by this aperture. In unstable resonators, a large number of longitudinal modes. Modes mean that is the modes corresponding to different wavelength. So in a stable resonator or in an unstable resonator, a large number of longitudinal modes may operate. And this may correspond to a single transverse mode due to axial and non-axial field propagation. Single transverse mode, actually this is the transverse mode, which is actually the cross section of the beam perpendicular to the direction of the z-axis, or perpendicular to the direction of the cavity axis or the resonator axis. That is called the transverse direction. And if you chop a laser beam, then of course the cross section will give you the transverse mode. And the transverse mode is actually in case of unstable resonator, it is contributed both by the non-axial field propagation and by the axial field propagation. Whereas in the stable resonator, only the axial field propagates towards the transverse mode. The non-axial part of the field undergoes greater geometrical losses as the rays leak out of the cavity. If the loss due to the walk of rays, that is those rays which are leaving the cavity, could be converted to contribute in the output beam, then this may result in the positive use of unstable resonators. So you see that in the unstable resonator, the main problem is that we have the non-axial field, that is the field which is living, which is not propagating along the axial direction, but is moving away from the axial directions. And in that case, that beam results in the form of a loss. So if we somehow could convert that non-axial field towards the axis, or could convert it to contribute in the axial direction or in the output beam, then this may result in the positive use of the unstable resonators. In stable resonators, the losses in the cavity are mainly due to diffraction. Next, we discuss the unstable resonators with the geometric optics point of view. In unstable resonator, the field is not Hermite-Gaussian type as in case of stable resonators. This Hermite-Gaussian field is what we have discussed in many of the previous slides. The beam is not focused towards the resonator axis. In case of geometric optics point of view, that is in case of unstable resonator, the beam is not focused towards the resonator axis because it spreads out over the transverse dimensions of the resonator, and the field acquire constant amplitude over the resonator cross section. So you see that in the unstable resonators, we have the contributions from both the axial directions and from the both axial field and both the non-axial field. So both contribute at the dimensions of the transverse dimensions of the resonator, and the field acquire constant amplitude over the resonator cross section. The field, however, is of spherical type, and the two counter propagating spherical waves exist in the unstable resonator. So you see that we have two spherical waves generated by mirror 1 and mirror 2, or reflected by mirror 1 and mirror 2 within the resonator. So both will move in opposite directions and they can couple each other, forming a standing waves. A mode in the unstable resonator is due to the superposition of these spherical modes. The modes, you see that we talk about the modes, these are actually the longitudinal modes, and these longitudinal modes in the unstable resonator is due to the superposition of these spherical waves. The complex beam parameter Q, which we have been talking about as the complex parameter in our previous slides, now this Q will be positive. This will correspond to two spherical waves. So let me describe this figure. That's the figure number 2. A general two-mirror unstable resonator with the spherical waves appearing to emanate from P1 and P2. So you see that this resonator, which is an example of an unstable resonator, has a mirror 1 labeled by 1 and mirror 2 labeled by 2. The mirror 1 has a dimension of 2a1 along the transverse direction, and the mirror 2 has a dimensions of 2a2 along the transverse directions. That is, the radius along the transverse direction for the mirror 1 is a1, and the radius of the mirror 2 along the transverse direction is a2. And P1 is the radius of curvature for the mirror 1, and P2 is a point which is the radius of curvature of which is the center of radius of curvature for the mirror 2. So the separation between the mirror 1 and the mirror 2 is given by capital L. The point P1 is located behind the mirror 1 and has a separation equal to R1L. So this R1L is actually the radius of curvature of the mirror 1. And on the other side, we have R2L, which is the distance from the mirror 2 to the point P2. So this may be referred to as the radius of curvature for the mirror 2. You see that the light from the light from P2 appears to be spherical, passing through the mirror 2, and you see that this is incident on the mirror 1. But you know that the diameter of the beam from the mirror 2 towards mirror 1 is larger than the dimensions of the mirror 1. So it means that the rest of the beam, some beam will be reflected by the mirror 1 as shown by the two arrows, and you see that the other part of the beam which is not intersected by the mirror 1 will leak out of the laser cavity on this end. That is on the left hand side, the light will leak out. And similarly, the light which is reflected by the mirror 1 towards the mirror 2 is shown by the two rays forming a cone of rays. And I have shown two extreme rays from the mirror number 1. So the diameter of this cone at the location of the mirror 2 is represented by capital M12 times 2a1, where 2a1 is the diameter along the transverse direction of the mirror 1 multiplied by M12, which is the magnification. So M12 is the magnification when the light beam travels from mirror 1 to mirror 2. So you see that this cone of light which is reflected by the mirror 1 is also much larger than the dimensions of the mirror 2. So the light will also leak out from the cavity, from the resonator, from the mirror 2. So in this particular configuration, light will leak the resonator or will leave the resonator on both ends. That is at the aperture of the mirror 1 and also at the aperture of the mirror 2, because the dimensions or the diameters of these beams at the location of the mirror 1 and at the location of the mirror 1 are larger than the sizes of the mirrors. So these lights or the fields or the rays will leave the resonator or will leak out the resonator from both ends. So let me give you the description in words for this picture. Consider a general two-mirrored unstable resonator with spherical waves having P1 and P2 as the centers of curvature. This is shown in figure number 2, that is in this figure. So P1 and P2 are the centers of curvature. A spherical wave from P1 incident on the mirror 2 will be reflected as a spherical wave from P2. So a spherical wave from P1 will be incident on the mirror 2 and will appear to be reflected from the point P2. Similarly, the spherical wave originating from P2 will be incident on the mirror 1 and will be reflected as if originating as a spherical wave from P1. The point P1 is behind the mirror 1 by a distance equal to R1L, and the point P2 is behind the mirror 2 by a distance equal to R2L, where R1 and R2 are the dimensionless quantities. There will be two equations in two unknowns, R1 and R2, which can be expressed in the cavity parameter G as. So you see that G are the cavity parameters, and G and G1 and G2 are what we have drawn in equation number in figure number 1. So these are the G parameters, and the product of G1 and G2 is referred to as G only. So here you see that we are representing over 1 over 1, 1 over R1 and 1 over R2 in terms of the G parameters of the cavity. So for equation number 1, we have 1 over R1 is equal to G1 times the square root of 1 minus 1 over G1 G2, and outside that square root we have a plus G1 minus 1. Similarly, for equation number 2, we have 1 over R2 is equal to G2 times the square root of 1 minus 1 over G1 G2, and outside that square root we have a plus G2 minus 1. You see that here G1 is actually 1 minus L over R1L, and G2 is equal to 1 minus capital L over R2 capital L. So you see that because you know that the formula for G1 was 1 minus L over R1, and R1 over here is R1L. So G1 is equal to L over 1 minus L over R1L, and similarly G2 will be equal to 1 minus capital L over R2L. So if you use those values of G1 and G2 as I described, you can get that the output is also equal to 1 over R. So this is what we have represented 1 over R1 and 1 over R2 in terms of the G parameters of the resonator. Let us introduce M12 and M21 as the magnification of the spherical waves in going from mirror 1 to 2 and in going from mirror 2 to 1 respectively. Their relationship with R1 and R2 can be obtained as M12 is equal to 1 plus 1 over R1 and M21 is equal to 1 plus 1 over R2. So if you want to find out the magnification, what you need to do is that you have R1L plus L1 divided by R1L. And for the magnification M21, you have capital L plus R2L divided by R2L. So these will give you the magnifications which I have shown in equation number 3 and 4. So let me discuss this figure, and in the description I shall give you a detailed analysis of this figure. So this figure is also so let me read the caption first. A general two-mirror single-ended unstable resonator with spherical waves emanating from P1 and P2. So in this figure and the figure that I have presented over here, there is a small difference. Look at the rays which are reflected from mirror 2 at the location of mirror 1. The diameter of these rays, that is this ray and this ray, you see that is greater than the dimensions of the mirror 1. But you know that in over here in this figure, the dimensions of the rays reflected from the mirror 2, these rays at the location of the mirror 1 has the same dimensions as that of a mirror 1. That is the light which is incident from the mirror 2 towards the mirror 1. All the light is reflected out of the laser cavity, out of the resonator, and no light will pass through or will leak the resonator from the end of the mirror 1, because the mirror 1 will reflect all the light it receives. So this is what it is called a single-ended unstable resonator, because only one end, that is the aperture at the location of the mirror 2, will allow the light to leave the cavity, and the cavity light will not be leaked from the mirror, from the location of the mirror 1. That's why it is called a single-ended unstable resonator. So this was the only difference between them. Let us complete these quantities to a single-ended unstable shown in figure 3. Let us correlate these quantities to a single-ended unstable resonator shown in figure 3. So the quantities that we have mentioned, that is the magnification or the parameters of the R1 and R2, let's now correlate them with the single-ended unstable resonator. The transverse extent of the spherical wave incident on mirror 1 should satisfy the condition that A1 should be greater than M21 times A2, where M21 is actually the magnification when the light will, or when the field will travel from the mirror 2 to the mirror 1. So this magnification is given by M2, and A2 is actually the radius, the transverse radius of the mirror 2. So the product of these two quantities should be less than, or in other words, the transverse radius of the mirror 1 should be, that is A1 should be greater than M21 times A2. so that all the light which is incident on the mirror 1 is reflected off the mirror 1 out, and the rays could be reflected towards the mirror 2, and also some of the rays will leave the resonator. So this condition must be satisfied for the resonator to be a single-ended resonator. So A1 must be greater than M21 times A2. The beam reflected from mirror 1 seems to originate from P1, which will leave the laser resonator at mirror 2. So the light will leave only at the location of the resonator mirror 2. This is true when both mirrors are 100% reflected. So you see that the mirror 2 and mirror 1 are 100% reflected. It means that when the light will incident on the mirror 1, the light will not get through the mirror 1, but is totally reflected in the form of the rays, as you can see. And some of the light is also reflected towards the mirror 2. And you see that mirror 2 is also a 100% reflector. No light will pass through the mirror 2 towards the right, that is towards the point P2. So all the light incident on the mirror 2 is reflected off towards the mirror 1. But you know that the light which is reflected off the mirror 1 is intercepted by the mirror 2, and the light which is not intercepted by the mirror 2 will leak out of the resonator. The spherical wave originating from P2 has a diameter equal to 2A2 at the mirror 2, which after one round trip is magnified by a factor m given by. So capital M is equal to M21 multiplied by M12, and you know that these are the magnifications that we have calculated earlier. So substituting their value, we have in the parenthesis 1 plus 1 over R2 multiplied by 1 plus 1 over R1. So what is the meaning of this magnification? Actually, this magnification is the magnification M21 is the magnification when the field travels from the mirror 2 towards mirror 1. And M12 is the magnification when the field travels from mirror 1 towards mirror 2. So the product of these two magnifications, capital M, is shown over here. So this is capital M, you see. And you see that this capital M is being multiplied with the 2A2, that is the dimensions of the mirror 2. Because here we are starting from mirror 2, that is the light will leave mirror 2 towards mirror 1. So the magnification will be M21, and from the mirror 1 the light is reflected off, and then the magnification will be M12. So the product of these two magnifications is actually capital M, and this is multiplied by 2A2, because of course the magnification will be multiplied by this diameter of the mirror M2, so that you can get this total diameter of the aperture shown within the two, shown by the width of the aperture shown by the quantity capital M times 2A2. Okay, so this capital M in terms of the G parameters is given by capital M is equal to 2 times of G1, G2, and within the parenthesis we have 1 minus 1 over 2 times of G1, G2 plus square root of 1 minus 1 over G1, G2. So this is equation number 5. And you know that this is G1, again G1 and G2 we have described earlier. That is G1 will be equal to, in our case, G1 will be equal to 1 minus L over R1 L, and G2 will be equal to 1 minus L over R2 L. And so we have represented capital M, that is the magnification, in terms of the G parameters shown in equation number 5. Where G1, G2, that is the product of these two G values, G1, G2, which we simply call as G, is less than 0 when capital M is less than 0. The beam leaving the mirror 2 has uniform illumination. If we define the beam cross section at mirror 2 as S2 is equal to pi A2 square, you see that the radius is A2 and the area of the mirror that will contribute is pi times A2 square. So S2 is actually the area of the beam cross section from the mirror 2. And after one round trip, we can say that at the location of the mirror 2 we have the area which is given by S2 prime, which is equal to pi multiplied by m square times A2 square. where m square mean, because since we are talking about the area, m stands for the magnification for one transverse dimension. For the area dimension, we have m square. So that's why we have a pi into m square times a2 square. You will see that here we have applied multiplied 2a2 with a single power of m, because here we are considering the linear dimension of the aperture diameter 2a2. But you know that here we are considering the area, so that's why we are multiplying it with the a2 with the m2 square. Sorry, with the m square. So we have A2 prime is equal to, this is the area of the field that will be at the location of the mirror 2 when it completes one round trip. That is, it goes towards the mirror 1 and after reflected by the mirror 1, and then the field will reach at the location of the mirror 2, and the area of that spot will be S2 prime is equal to pi times m square multiplied by A2 square. Then the cavity loss gamma after one round trip is defined as, so gamma is equal to S2 prime minus S2 divided by S2 prime. So substituting the values of S2 prime and S2, we have gamma in terms of the magnification parameters, which is m square minus 1 over m square, which is independent of the diameter of the mirror 2. And m square is what we have defined over here in terms of the g parameters, or in terms of the radius of curvature, we have defined m over here. So we have defined gamma, which represents actually cavity loss in equation number 6. Now you see that now we are going to moving forward, and we are presenting the wave optics description of unstable resonator is now presented. To determine the modes in an unstable resonator, wave approach is used as a Huygens-Fresnel diffraction integral. You see that we have also presented Huygens-Fresnel diffraction integral in when we were dealing with the stable resonators. So look all the previous presentations on stable resonators. There you can find out the Huygens-Fresnel diffraction integral. In an unstable resonator, when we are talking about the wave optics, the output mirror with the limited size forms important features of the resonator. Because here the output mirror over, for example, is mirror 2, it has a limited dimensions, whereas the size of the spot after one round trip represented by the magnification capital M is much larger than the linear dimensions of the mirror. The propagation kernel capital K or kappa can be found, and the integral is solved in the same fashion as done for the stable resonators. An integral based on the Huygens-Fresnel integral is given by. So this is the integral that we have discussed in equation in slide number 83 and equation number 6. So let me read that one. It has sigma prime multiplied by e prime of x comma y comma 0, and on the right hand side we have the double integral containing a field e prime at the location of x1 y1 0, and then multiplied by the kappa, which is x comma y and x1 and y1, and the integration variables are dx1 and dy1. Where you see that e prime of x1 y1 0 is actually the field at the location of the mirror 1, and then after one round trip where the field will repeat itself, we have the quantity, that is the field on the left hand side after one round trip, which is given by sigma prime into e prime of x comma y comma 0. So this field after one round trip is related with the field initial field, which is e prime of x1 y1 and 0, through the Huygens-Fresnel integral shown in equation number 7. This integral is also applicable to unstable resonator, for which eigensolutions or the field repeat itself after one round trip. Using the geometric optics approach, it has been established that the output beam intensity in an unstable resonator is constant. So you see that in case of unstable resonator, using the geometric optics approach, we find that the magnitude of the field leaving this cavity at the location of the mirror 2 has a constant intensity at this location for the beam which leaves the resonator. And you know that the beam 2 will actually intersect, the light will not pass through the mirror 2 because mirror 2 is a 100% mirror. But of course you see that the diffraction will take place at the edges of the mirror, so the light will also be contributed at the location behind the mirror 2. But you see that the intensity is in, according to the geometric optics, the intensity has to be constant when living on the end of the mirror 2. In wave optics, so you see that according to geometric optics, the output beam intensity is constant in an unstable resonator. So what about the wave optics approach? What about the intensity of the beam coming out from the resonator when we are dealing with the wave optics? So what will be the scenario in that case? In the wave optics approach, the output intensity description over the beam cross section in an unstable resonator is quite different and is shown in figure 4. For the case of a positive branch single-ended confocal resonator, you know that when we are talking about positive branch, it means that either we are talking about the quadrant number 1 where the product of G1 G2 is greater than 1, or we are talking about the third quadrant where G1 the product of G1 and G2 is also greater than 1. So you see that we are talking about the magnification m is equal to 2.6 in this case. In this particular case, the simulation results are presented. So for the case of a positive branch single-ended, you know that single-ended means I have explained that only the light will leak out or the output will be obtained from the side of the mirror 2, not from the end of the mirror 1. So this is the single-ended. So for a positive branch single-ended confocal resonators with the capital M is equal to 2.6 and the equivalent Fresnel number calculation using M is equal to 2.6 and using the other parameters of A2 and lambda and wavelength of light, which we have not presented over here, the NEQ, that is the equivalent Fresnel number, is equal to 0.65. So for the simulated results, we have the intensity plotted on the vertical axis and the dimensions of the aperture of the transverse aperture at the mirror 2 is represented by the parameter A2. So you see that here we are plotting x in terms of A2. So x will be minus A2 because we have -1 and we have a +1. The minimum value is -1, the maximum value is +1. It means the x has got minimum value equal to -A2, the maximum value is +A2. That is the total dimensions of 2A2 is actually the dimensions behind is actually the dimensions of the mirror. So we are talking about this. But you know that we have to take into account the magnification of the system also, because you see that this system has a magnification capital M. So we are not only going to discuss the field at the mirror 2, but also we are going to discuss the field at the whole aperture because of the magnification is also involved. So the caption is output intensity profile from a mirror 2 of a single-ended positive branch resonator. Vertical lines indicate the size of the mirror. So these are the vertical lines which indicate the size of the mirror, and the size of the mirror in this case, in this simulated results, is from -0.5A2 to +0.5A2. So this is the size of our mirror in the simulation. So x is equal to from -0.45A2 to +0.45A2. This is the dimensions of our mirror. And the other dimensions is, you see that -A2 to +A2. This is the whole aperture. This is actually the transverse cross section of the beam coming out on the end of the mirror 2, from the end of the mirror 2. So you see that this part of the intensity, which is before the 0.45, this is due to, you see that the contributions due to diffraction within the cavity, outside the cavity. And this is also outside the cavity because the mirror of the cavity has the dimensions of this one. And you can see that we can also receive light behind the cavity, that is behind the mirror 2. You can also receive some light over there. And you can also see, you can also notice that there are rings in the intensity. If you look this intensity, this is a one-dimensional profile of the transverse intensity profile in the cross section of the beam at the output. But if you look whole beam in the form of a two-dimensional, you will see that these will appear to be rings in the two-dimensional plot. And you know that in this one-dimensional plot, it appears as you see that these are small peaks, but these are actually the rings in the laser output when we view the output from the resonator in the form of a two-dimensional profile. So you see that this on the left hand side of this vertical line is the profile which is outside the resonator, that is which is beyond the dimensions of the width of the mirror. And on the right hand side, that is on this side, we have also a region which is beyond the dimensions of the mirror too. So a single-ended focal unstable resonator with a positive branch is shown in figure 5. This is figure 5. And you know that the unstable, that is the confocal unstable resonator, which we talked about over here, for which we have plotted this intensity. You see that we have also shown the description of that over here. A single-ended confocal unstable resonator with a positive branch is shown at the top, and with a negative branch is shown at the bottom. And the caption of the figure is single-ended unstable resonator at the top for positive branch and bottom for negative branch. Both are single-ended, but one is for the positive branch, and at the bottom we have the for the single-ended resonator for the negative branch. So you see that, let me explain briefly this one. The dimensions of the mirror 2 is again 2a2, the vertical dimension or the transverse dimension, and similarly the transverse dimension of the mirror 1 is 2a1. So I have shown only the point P2 over here. It appears as if the light is spherically generated by the point P2 and pass through the mirror 2. Then of course incident on the mirror 1. The mirror 1 reflect back towards the mirror 2, and also some light also going out of the resonator dimensions, because the beam is spreading out, you see, when reflected off the mirror 1. And here you can see, here you can also notice that the location of the radii of curvature, that is the focal point, that is the center of the radius of curvature for the mirror 1 and the mirror 2 are at the same location. For the mirror 1, it is referred to as f1, taken as a positive, and for the mirror 2, it is referred to as f2 star. But you see that both have the same, that is mirror 1 has the same focus point, focal, that is the radius of curvature for the mirror starts from point P2, and similarly the radius of curvature for the mirror 2 starts from point P2, but it is labeled as f2 prime, f2 star over here. So you see that for this system we have defined the magnification, that is A1 is equal to 2.6 times A2. That is the dimensions of over this mirror A1 in radius form is equal to 2.6 times the radial dimensions of the mirror 2 as given over here. Because you see that we are using this system for a magnification of 2.6. So it means that the dimensions of the mirror 1 should be 2.6 times the dimension of the mirror 2. So that all the beam is intersected by the mirror 1 and is reflected off towards the mirror 2. And you see that this is the negative branch, but single-ended unstable resonator. So you see that you can see the focus point in aligned within the resonator. So F1 is the focus point for the radius of curvature of the mirror 1, and F2 is the focal point for the radius of curvature for the mirror 2. And you see that these two also coincide over here, because we are talking about the confocal resonators. So this is also a confocal resonator, this is also a confocal resonator, because both have the same focus point, or the points where the center of radius radii of curvature are the same for the both systems. The intensity just in front of mirror 2 propagating to the right out of the cavity with vertical lines indicating the side of the mirror 2 is shown in figure 4. You see that here what I have shown over here. I have also shown that these represents these vertical line represent the location of the mirrors, and this is the separation between these two vertical lines. This is the separation between the two between the two sides of the output mirror. That is the one that is the mirror starts from, and mirror 2 starts from at the location of -4.582 and then ends at plus of 0.45. So this is the size of the mirror 2, and the rest of them is actually the full aperture from which the light will exit, and that full aperture is actually represented by m2 times of a2. So this is the full aperture starting from here and ending over here. And then you see that this is the size of the aperture of the mirror 2, which we have represented as the two vertical lines in this diagram in figure number 4. So we are giving this description about the figure 4. The beam within the vertical lines is reflected by the mirror 2 towards the mirror 1, whereas the rest of the beam is transmitted as output beam. After one round trip, the part of the beam within the vertical lines is regenerated as the full beam due to the spherical divergence and diffraction. So you see that since we are talking about the field, we can talk about the divergence, and we can also particularly talk about the diffraction, because we are talking about the field, and due to the diffraction, the field is also contributing not only within the mirror, and but also contributing outside the mirrors, outside the dimensions of the mirror. So the field due to the divergence and due to the diffraction of the field within the resonator, and also particularly at the location of the mirror 1, these will contribute the field not only at the location of the mirror 1 but also outside the location of the mirror 2, out of the size of the mirror 2. So this in the output beam profile, many diffraction rings are observable due to diffraction by the edges of the mirror 2. So you see that when the light will leave at the end of from the end of the mirror 2, you see that the mirror 2 is present, and the field is also leaking out from the mirror 2. So some of the light will also hit the mirror 2. And you know that when the diffraction will occur at the mirror 2, so the diffraction will contribute at the back of the mirror 2, but also at the outside away from the mirror 2. So due to that one, the ringing effect will appear, that the rings will appear. And these rings are actually due to the diffraction at the edges of the mirror 2. And these diffractions, it means that the field will also, due to these diffractions, the field also contributed at the back of the mirror 2 and also outside the dimensions of the mirror 2. And of course, you can see the rings also when the light leaves outside the mirror 2, outside the dimensions of the mirror 2. The output wavefront in this particular case is plane, that is having the same phase, which in other general cases is found near spherical. So you see that the particular case that we are considering over here, we have the case in which we find that the plane that the wavefront is a plane wave coming out from the end side of the mirror 2. But in general, it is found that it should be a nearly spherical. Both approaches agree over it. That is, in the geometrical optics case, we have seen that the wavefront should be spherical, and in this case, in the case of the wavefront approach, we also see that the wavefront should be spherical in nature. But only in our particular case that we are presenting over here, the wavefront is plane. but in general it should be spherical. So this spherical wavefront is being supported by the wavefront theory and also by the by the wave field phenomena and also by the geometric optics phenomena. The phase variation over the wavefronts is found similar in the two approaches, that is in both approaches, geometric optics approach and the physical optics approach. Different transverse modes can oscillate in an unstable cavity. Different transverse mode mean TEM0, 0 mode, TEM01 mode, TEM10 mode, and of course other modes. These are the transverse modes. So different transverse modes can oscillate in unstable cavity and are hard to distinguish clearly and are quite different from those of the stable resonators. So you see that as far as the two approaches are discussed, that is the geometric approach and the field optics approach, we see that it is hard to distinguish between those modes clearly, but there is of course a definite distinction that we can make with the field coming out with the modes for the case of the stable resonator. First three modes for the positive branch confocal unstable resonator are shown in figure number 6. That is in this figure. And of course, this is the figure that we have drawn for the case of a confocal unstable resonator for the positive branch. In the L is equal to 0 mode, the field is more concentrated towards the beam axis and undergoes a minimum loss, and thus regarded as the fundamental mode of the unstable resonator. You see that L is equal to 0 mode, field is more concentrated towards the beam axis and undergoes a minimum loss, and thus regarded as the fundamental mode of the unstable resonator. So you can see the you see that I have this is the origin, this is the center point of the aperture, output aperture from which the beam will come out, and from this center to the point A, this is the dimensions of the mirror, and beyond that one there is an aperture from which the mirror will come out, from which the light will come out, and you will see that the light with L is equal to 0 order has the maximum value within the dimensions of the aperture, and after that you see that this order is going to decrease in intensity because on the vertical side we are plotting the intensity, and you see that consider the L is equal to 1 order. The L is equal to 1 order. You see that at the center of the length, at the center of the mirror, it is completely 0. But if you move away from the center, you can find out that this starts contributing, and but you know that this is diverging. You see that this is going to increase, and it increases to some point within the dimensions of the mirror, and then you see that beyond the mirror it will keep on increasing and becomes maximum outside the dimensions of the mirror, and then of course you see that after some value it will keep on decreasing, and of course after the you see that we have a maximum, consider the dimensions of the aperture up to MA, and you see that even it is going beyond the value of MA. And similar, consider the mode L is equal to 2. The L is equal to 2 mode represented by the large dotted lines. You see that it has some definite value at the center of the mirror. Then of course it will decrease, and then it slightly increases. And then you see that after that, after the dimensions of the mirror, it starts on increasing, reaches to some maximum value within the aperture of the size MA, and then you see that after that one, it will keep on decreasing. And after the size of MA, it will of course vanish out as some region. So from 0 to A, it is the region for the radius of the mirror, and from 0 to MA, it is the full aperture that we are considering. And then from 0 to onward, beyond the value of MA, it is the aperture that lies further outside. And the caption of figure 6 is intensity profile of the first 3 eigen modes in an unstable resonator with M is equal to 2.6 and N equivalent, that is the Fresnel equivalent, equivalent Fresnel number NEQ is equal to 0.7. So with this data, we have plotted these curves for the L is equal to 0 mode, for L is equal to 1 mode, and for L is equal to 2 mode. That is the first three modes. And you can see the intensity of these modes also. And in the description, I have said that in the L is equal to 0 mode, the field is more concentrated towards the beam waist, because the beam waist is the waist just after the mirror 2. And the most you see that is the beam is more concentrated, that is has a maximum value. You see L is equal to mode has the maximum value, that is the beam waist. At the beam waist we shall have the maximum value of intensity. So L is equal to 2, L is equal to 0 case is actually forming a beam waist at the mirror. That is within the resonator. So in the L is equal to 0 mode, the field is more concentrated towards the beam waist and undergoes a minimum loss within the beam waist. Of course, the loss is minimum because here the intensity is maximum and thus regarded as the fundamental mode of the unstable resonator. Because for L is equal to 0 mode, it is maximized within the region of the size of the mirror. So it is maximized over here, forming a beam waist, and of course the loss is minimum for this one. So that's why L is equal to 0 mode is regarded as the fundamental mode. The magnitude of the eigenvalue sigma mod versus the equivalent Fresnel number NEQ for the first three modes is plotted in figure number 7. The NEQ can be changed by changing the value of M, A2 and capital L. So you see that the Fresnel number, equivalent Fresnel number, can be changed when we either by changing capital M, that is the magnification of the system, either the size of the mirror 2 or the separation between the cavity mirrors, capital L. And you see that this is what we are plotting sigma mod versus N versus the equivalent Fresnel number in figure number 7. That is in this figure. So sigma has been plotted, that is the eigenvalue has been plotted on the vertical side, and we are plotting the Fresnel equivalent number on the horizontal dimensions. So the caption of the figure is a plot of eigenvalue magnitude sigma mod versus the equivalent Fresnel number NEQ for the first three modes, that is for the L is equal to 0 mode, L is equal to 1 mode, L is equal to 2 mode. So there are some important points about these modes. For example, the peak of these modes occurs at half integer values. For example, L is equal to 2, the peak of corresponding to L is equal to 0 occurs at 0.5. The peak corresponding to L is equal to 1 mode occurs at 1.5, that is 3 by 2. And the next peak of the mode L is equal to 2 occurs at 2.5. The peak corresponding to L is equal to 2 mode, the first peak corresponding to L is equal to 2 mode occurs at 3.5. And so on. And you see that the neighboring, there is interaction, that is the two waves interact each other. For example, this interaction point occurs at integer values. For example, the mode L is equal to 0 and mode L is equal to 1 meet at this point, which corresponds to value of NQ equal to 1. And you see that if you look at the second one, for example, the L is equal to 1 mode also meets the L is equal to 0 mode for the second time, but at a value corresponding to n value equal to 2. And similarly, the L is equal to 0 mode meets the L is equal to 2 mode at the value which corresponds to n equivalent value equal to 3. That is the Fresnel number equal to 3. So these neighboring meets at integer values of n equivalent. Okay, so this is what I am talking about, equation number, figure number 92.7. So further about that figure, when NEQ increases from 0.6 in the range of this one, that is from 0.6 to 1, for this value of n, the mode L is equal to 1 starts contracting towards the resonator axis, whereas the mode L is equal to 0 starts spreading out. So you see that in this region, that's from 0.6 to 1. Look at this one. From 0.6 to 1, the peak occurs at L is equal to, the peak of L is equal to 0 occurs at 0.5, and after that one, that's from 0.6 to onward, it will moving away from the resonator because its value is going to fall. Whereas the L is equal to 1 mode starts increasing, that is starts contributing towards the beam axis. So when the value is increasing, it means that it starts contributing towards the beam axis, and when the value is decreasing, it means that it's moving away. Its contribution is moving away from the beam axis. The L is equal to 1 mode behaves as the lowest order mode, that is a mode with the lowest loss when N equivalent lies in the value of 1 to 1.5. So you see that in the region of 1 to 1 plus 5, the value of L1 is going to increase and it becomes a maximum. You see that. So it means that its contribution towards the cavity or towards the cavity axis or towards the resonator axis is going to increase and it becomes maximum over here. It means that the loss of this mode within the resonator in the region from 1 to 1.5 is maximized. And you see that after that it will decrease. The mode L is equal to 0 is the lowest mode when N equivalent is less than 0.5. So if you consider N equivalent less than 0.5, where N is equal to 0 mode is starts to increasing drastically, it means that its contribution, that L is equal to 0, starts contributing towards the beam axis and maximized at the value of N equivalent to 2.5 value. So you see that this is what I have given a brief description in terms of the change in value of the Fresnel equivalent value versus the intensity or versus the eigenvalue for these three modes. With the change in value of the N equivalent, the modes interchange their roles. You see that mode will interchange their roles. That is, L is equal to 0 becomes a maximum at some point. Then L is equal to 1 becomes a maximum at some other value of NQ. Then L is equal to 2 becomes a maximum at some other value of NEQ. So with the change in the value of NEQ, the modes interchange their roles. The transverse mode discrimination is largest when N equivalent is equal to half integer values. So look at half integer values. That is L is equal to 0, peak occurs at half value which is 1 by 2. Similarly, L is equal to 1, peak occurs at 3 by 2, which is 1.5. Similarly, L is equal to 2 occurs at a value of 3.5, and so on. And you see that these are the transverse mode we are talking about. The transverse mode discrimination is largest when NEQ is equal to half integer values. In terms of large difference between losses of modes. So you see that when these modes reaches the peak values, it means that the losses are minimized. For example, in the region from N is equal to EQ from 0 to 0.5, the loss for the L is equal to 0 mode is decreasing, and you see that loss becomes minimum at the peak of the L is equal to 0 mode. So in terms of the large difference between the losses of the mode, that is the transverse mode discrimination is largest when N equivalent is equal to half integer values in terms of the large difference between the losses of the modes. The curve cross section over the neighboring, the curves cross over the neighboring mode curves when NEQ takes integer values. So look at this crossover over here, where L is equal to 0 and L is equal to 1 curve are crossing each other. So this is the crossover, and it occurs for integer values of N equivalent. So for example, the first crossover between the two curves occur for N is equal to 1. The second crossover occurs between the L is equal to 1 mode, L is equal to 0 mode, and L is equal to 1 mode at the value of n equivalent to 2. And the third crossover occurs at a value of n equivalent to 3 between the L is equal to 0 mode and L is equal to 2 mode. The intensity of modes predicted by the wave optics is different from those of the constant value determined by the geometric optics. So the intensity values you see that are different in case of the wave optics approach and in case of the geometric optics approach. But you know that one thing was common, that both will have a spherical wavefront. And in the particular case that we have presented in our presentation, the wavefront was plane. But you know that in general, the wavefront is spherical in both approaches. In the lowest order mode, the field is concentrated towards the beam axis. For example, when the peak is approaching the highest value, it means that it is being concentrated at the beam axis. So I think that I have given a detailed description, and it covers both the analysis of the unstable resonators with respect to geometric point of view and with respect to the wave optics point of view. So this is the end of slide number 92.